Morning, everybody. We're going to try this again today. I think it'll work this time. I realized that I needed to get a bigger flame, so I'm going to light paper today, and hopefully we'll see it work. Well, if this will light, we'll see. And it's going now. Okay, so we'll get a good flame going, and hopefully it'll stay in the jar and we can see this happen. And so if you want to make the flame bigger, you always put the fuel above. And so in this case, paper is the fuel. And so if you have a match, say you want to make the flame bigger, you always put the wood on this part. If I were to turn around upside down, you wouldn't get a very good flame. Well, I think I waited too long. Well, it started to go and then it stopped again because once again, I didn't get the flame going. So I guess this paper is not very flammable. Let me try paper towel instead. Well, sorry, I thought that was going to work this time. I should have checked to make sure that paper would actually light on fire and stay lit on fire. See if this works better. I think this will work. Okay, so you can see now the egg is being pulled into the jar. So why is that happening? We had in here with the flame a higher temperature than outside. But with the egg on top now, the flame goes out, it starts to cool back down. And what we learned yesterday with Gay-Lussac's law is that with lower temperature, you have lower pressure. And so you create a lower pressure area in here when the flame goes out, higher pressure out here. The higher pressure air pushes the egg into the jar. So this demonstrates Gay-Lussac's law. With you change temperature, you change the pressure. In this case, the egg is pulled in. Okay, well, that took 5 tries, but we finally got it to work. Go ahead and get this pulled back. I'm gonna put the whiteboard on, and we'll do a few things today in chapter 13.3. And today will be our last day of actual lessons. Tomorrow we're gonna talk about a lab we'll be doing on Friday. If you have any baking soda or vinegar, just get that ready for Friday. Again, it's purely optional, you don't have to, but I think it's a really fun lab, and so if you have that, and also a sandwich bag or a quart size bag, like a plastic bag. So you would just need 3 supplies, and then a measuring thing like a teaspoon or a tablespoon measuring. So tomorrow I'll go through the lab and tell you how to do it, and then Friday we'll do the lab for those who want to. Okay, so for today, we'll talk about Avogadro's principle to start off with. Also called Avogadro's law, just depends on what book you're reading, whether they say law or principle. I think your book says principle. And what he said is this, that equal volumes of gas contain equal numbers of moles. Provided at the same temperature and the same pressure. So equal volumes of gas at the same temperature and pressure contain equal numbers of moles, or in this case, particles. It's the same thing. So it's based off this principle that if you were to have a container, let's say helium, Yeah, let me draw this bigger. So gas particles are very far apart from each other. If you were to have one gas atom 5 feet in diameter, so like think of my classroom, you have that black filing cabinet in the corner. That's roughly 5 feet in diameter. So imagine that black filing cabinet in my classroom as one atom. The next atom past that would be 50 feet away from it. So think of where my oven is in my classroom. And that's how far the next gas atom would be. The one after that would be 5 stories above those two atoms. So that's how far apart gas atoms are from each other. There's a lot of empty space between them. And because of that, it doesn't really matter if it's a big or a small atom. So helium is a pretty small atom. But if you think of, say, xenon, it's a much more massive atom. So helium's molar mass is 2.02 grams per mole. Xenon's molar mass is 131.29 grams per mole. So xenon is about 60 times more massive than helium is. But it doesn't really matter as far as talking about the volumes of gas and their particles, because they're still so far apart, it wouldn't make a difference in how many you'd have in a sample size. And so what this says is that if you take a certain volume of gas, you'll have the same number of particles of gas, whether it's a small particle like, say, helium, or a big one like xenon. In this case, we still have 2 particles. It's the same volume. In this case, we have 2 particles. Another way to say it would be like this. Avogadro knew this, that if you were to take 2 liters of hydrogen and react it with 1 liter of oxygen, you would get 2 liters of H2O vapor. And so that's how is the base of his principle. This experiment helped him format this principle. How did he explain this? You go from 2 liters and 1 liter, so that's a total of 3 liters, to 2 liters. How is that possible to go from 3 liters to 2 liters? And he explained it this way, that they are going from, well, I'll just write it out here. So on this side, we have a total of 3 moles. We have 2 H2s, we have 1 O2. On the right-hand side, we have 2 H2Os. The atoms just group differently. And that's how he explained it. That's why we go from 3 liters on this side to 2 liters on that side. The atoms break apart. In this case, the H2s become single H's floating around. So we have a total of 4 H's right here. The O's break apart. So now we have is 2 O's, 4 H's. These 2 H's right here bond to this O to make this water. Same thing here. And that's how we get 2H2O. So the amount of particles determines the volume. In this case, 2 liters represents 2 particles. 1 liter represents 1 particle. And because we have 2 particles on that side, we're going to have 2 liters of H2O. And so we said that volume is only due to how many particles you have and nothing else. What he also found is this, that 22.4 liters of a gas equals 1 mole of that gas. And that's true for any gas. Provided it's at a certain temperature. It has to be at standard temperature and pressure, which we'll talk about in a second. So 1 mole of gas is equal to 22.4 liters of gas as long as it's a standard temperature and pressure. STP is its abbreviation. The temperature is 273 Kelvin. That's 0 degrees Celsius. And then pressure is 1 atmosphere. So it has to be at normal atmospheric conditions. So that'd just be the normal pressure that you feel right now around you. And then temperature at 0 degrees Celsius, 273 Kelvin. So that's STP. And as long as you have a gas at that temperature and pressure, 22.4 liters of any gas will be equal to 1 mole of that gas. Okay, one last thing to go through today. It's called the ideal gas law. We talked actually about the combined gas law, which combined Gay-Lussac's law with Boyle's and Charles's law. The ideal gas law combines those ones along with Avogadro's law. So this combines Boyle's, Charles, the ideal gas, Gay-Lussac's law, and Avogadro's law. So basically, it's the combined gas law along with one more thing. And it looks like this. Pressure times volume equals nRT. Okay, so we know that P is pressure, V is volume, and T is temperature. N and R are new ones, so we'll go through those ones. N just stands for number of moles. And then R is a constant. Usually you're going to use this constant. There's a couple of ones you can use for R, but the one you're going to use most often would be this one, 0.0821. The units are liters times atmospheres over moles times Kelvin. So these units right here tell you what you have to have everything in your equation. So this tells you need to have volume in liters. So if your volume unit's not in liters, then you can't use this R. Atmospheres is the pressure unit. And so this tells you that you have to have a unit of pressure of atmospheres and a volume unit of liters to use it. There are other R's with different units. And again, I think you'll only really use this one in the book, but just in case, I'll write down one more R for you. Right up here at the top. So another R that you might see is 8.314 liters times kilopascals over moles times Kelvin. So all that's different between these two is the pressure unit. So if you've been given pascals, then you would use this R. If you're given liters, you'll use, or if you're given atmospheres, you'll use this R. So these are only two options for R. So if you were given pressure in, say, torr, 760 torr, you would have to convert that to atmospheres. And that there is 1 atmosphere in 760 torr. So that might be a conversion you'd have to do. Let me go through an example problem using this in your book on page 455. So it says on page 455, calculate the number of moles of ammonia gas contained in a 3-liter vessel at 300 Kelvin with a pressure of 1.5 atmospheres. Okay, so we're given the volume of the vessel, it's 3 liters. We're told the temperature is 300 Kelvin. and the pressure is 1.5 atmospheres. And they're asking for number of moles. So that would be N that we're trying to find. So if we're given variables with moles, pressure, temperature, and volume, we have to use the ideal gas law, which we went through today. So that's pressure times volume equals number of moles times R times temperature. So let's just plug in the values that we have. We're given 1.5 atmospheres for pressure, volume, 3 liters, number of moles, that's the unknown, R. So again, I gave you 2 R's, and almost always you're going to use the 0.0821. But if you forget which one to use, just look at the units. And it's liters times atmospheres over moles times Kelvin. And because we were given atmospheres for our pressure, we have to use this one right here. Now, I ran out of space over here, but we multiply it by temperature, multiply it by 300 Kelvin. And now we just need to solve for N. Okay, so on the left-hand side, we'll multiply 1.5 times 3. So what does that equal? Let's see really fast. 1.5 times 3. So we get 4.5. At this point, we'll keep the units together, so it's atmospheres times liters for right now. We multiply the units. Then on the right-hand side, we're going to do 0.0821 times 300. And that equals 24.6. So the units right here, notice that if we multiply Kelvin times this right here, the kelvins will cancel out. So now what we would have would be liters times atmospheres over moles. And then these two are multiplied times N. So we have N on the outside at this point. We want to solve for N, so divide both sides by 24.6. So what do we have now with the units? We can see that atmospheres will cancel out, liters will go away. Okay, so let's divide 4.5 by 24.6. We get 0.18. Now what happens to units over here? So what we have is 1 over mole, which if you learned in algebra, that would just flip around, and that would just become a mole. So we would have 0.18 moles. That equals N. And so that gives you the mole of the gas. Any questions about that? I'm going to clear this really fast. So one last thing before I leave today and give you some homework. We talked about this earlier, and Avogadro uses as proof of his principle. So just to be clear on what this tells you, this says a couple of things. So one thing we could say is that this is 2 molecules of H2O reacting with 1 molecule of O2 to make 2 molecules of H2O. We could say it's 2 moles of H2 reacting with 1 mole of O2. We could also say it's 2 liters if these are gases. So this is only true for a gas, but if we know these are gases, which they are, we could also say that the coefficient tells you how many liters are used. So in this case, 2 liters of H2 react with 1 liter of O2 to make 2 liters of H2O. So for any gas, we can also use the coefficient in front as liters. So this gives us a way to relate volume to moles. Okay, so let me give you a few homework questions to work on. Let me see really fast. So it's questions 27, 29 on page 455, and then 39 and 41. You write them on here. So it's questions 27 and 29. That's on page 455. And then 39 and 41. That's on page 461. Okay, so there was a really good question that was just asked about the R constant. You can have those on your note card with the equations. So I don't make you memorize constants. So definitely it would be a good idea to, along with your equations on your note card, to write down the 2 R constants that we talked about today. Sorry about that.